Hello, thank you for being here. I'm Esty Kelman, currently a postdoctoral researcher at BU and MIT. And today I'm going to discuss our results regarding sparse graph counting and Kelley Meka bounds for binary systems. This is a joint work with Yuval Filmus, Hatami, and Kaave Hosseini. Let me start with mentioning some important papers in theoretical computer science, and soon we'll discuss what is our results about. I want to mention some yearly paper from the 80s and one recent, all of them showing bounds for communication complexity for the number on forehead model. You might be familiar with the fast matrix multiplication by Coppersmith and Winograd. And another cool paper that I want to mention is efficient linearity testing by Hastad and Rigderson. And what I want to ask you is, what is common to all these papers? And it turned out that all of them based on constructions of dense sets that doesn't include three-term arithmetic progression inside. The study of such sets as inactive combinatorics were very extensive, and applications for theoretical computer science doesn't stop here. There are many for cryptography and sublinear algorithms, lower bounds for testing and streaming algorithms, and many others. And all of them would be benefit for having as large 3AP free set as possible. So what is the study of 3AP free sets? A three-term arithmetic progression is a set of three numbers that are equally spaced, for example, 3, 5, and 7. We can denote the first number by x1 and the difference by x2. And thus we can get a general pattern for 3AP, x1, x1 plus x2, and x1 plus 2x2. I know this is not the usual notation, but bear with me. And we say that a set subset of 1 to n is 3AP free if it doesn't contain any non-trivial 3AP. And what is non-trivial 3AP? Where all the three elements in the arithmetic progression are not the same, all distinct. And in this case, it means that x2 is not 0. The study of such sets started by a question raised by Erdős and Tuan asking what is the largest 3AP free set in 1 to n. So there are some easy observations. For example, if A is trivial, we know whether it's 3AP or not. If it includes the entire interval 1 to n, then for sure contains 3APs. If it's the empty set, then it for sure doesn't contain any 3AP. Non-trivial bound can come from a greedy construction when you take 1 and 2 and then skip 3 and add 4 and so on, skipping numbers that would complete 3APs with the previous chosen numbers. This would lead for a polynomial size 3AP free set. And the main investigation here is, can we hope for better constructions? In this work, we focus on generalizing Erdős-Tuan question to other linear patterns rather than 3AP. So what other linear patterns are? Which one we could consider? So this is a linear pattern of 3AP. We can think about longer arithmetic progressions. For example, for 4AP, we can add additional linear form, x1 plus 3x2, represent the next point in the sequence. We can think about another linear pattern of, we call it K4. This is linear pattern on 4 variables, where each pair appears in a linear form. So this is very associated with the for-click, when we can put, for every vertex, we can associate with a variable and every edge with a linear form that contains these two variables. In general, we might have several linear forms on k variables, and each linear form is a linear combination of the variables with integer coefficients. And we might think about various settings for the variables. They might come from the n. With when we take this instead of 1 to n, using the arithmetic modulo n to have some algebraic structure, you can think about vector spaces over finite fields. And we generalize the definition of 3AP free And we say that a set A is L-free if it contains no non-trivial instance of L, meaning that for any settings of the variables, we never get M distinct elements that are all in A. And the main question, generalizing the question by eradation to one regarding 3AP for every L. What is the largest L? The largest set that is L-free in 1-to-N. What do we know about 3AP? So the best constructions that are known till today are of the following lower bound, that large. And there are some recent improvements to Behrend construction, but this is only lower order terms improvement. So essentially, this is the order of 3AP free sets that we know since Behrend. Back to that days, it was not clear whether we can achieve a linear size 3AP free set. And then a few years later came what with his theorem showing that every 3AP free set must be sublinear in N. And up to 2021, the bounds that we knew are that any 3AP free set must be at most of density 1 over polylog N. And then in 2023, Kelley and Meka came with a big breakthrough, with a big jump forward showing a bound that almost closed the gap between upper bound and lower bound, and is exponentially better than all the previous. They developed many new techniques for their argument, and this later improved by Bloom and Sisask, refining the Kelley-Meka argument. And our main result in this work is generalizing the Kelley-Meka bound to a broad class of linear patterns. So what other linear patterns should we consider? What about 4AP? So it turned out that the question about 4AP is much harder than the question regarding 3AP, and all approaches for 3AP fails on 4AP. But it turned out that there are many other patterns that are somehow in between 4AP and 3AP in terms of their hardness or complexity. And an important class between them is the class of binary systems of linear forms. And in such linear patterns, every linear form depends on exactly two variables, looks of the form alpha xi plus beta xj, when alpha and beta are not zero. And no two forms depend on the same pair of variables. This is very related to simple graphs. Any such system we can represent in a graph. For example, K4 is a binary system. We can see that every linear form contains exactly two variables and no two shares more than one variable. The associated graph is, as we've seen, we put an vertex for every variable and edge for any linear form that depends on the pair of variables. Another example is 3AP is a binary system. So the following binary system is 3AP. You can see that if you take the first one and the last one, add them, divide by 2, you get the average of them is the middle one. And the associated graph is a triangle with vertices x1, x2, and x3, the variables, and for each linear form is associated with one of the edges. Our main result is showing Kelley-Meka bound for the binary systems. So formally, let L be a binary system. Think about fixed M, fixed system. If all translations of A are L-free, then A must be small. What do we mean by translations of A? We can take some element in Zn and think about the translation A plus H when we take every element in A and add H to it. And we want this to be L-free, meaning that for any settings of the variables, we never get M distinct elements, all of them in A plus H. And this would happen for every H. So one comment regarding the constant here. So this is a bit worse than what we saw that is best known for 3AP. But anyway, in our paper, we showed that for some subclass of the binary systems, which contains a 3AP, we can achieve the best known constant here for the binary systems for this class, and thus we recover the best known result for 3AP. Another thing that was mentioned is that this theorem holds for any finite abelian group, in particular for vector spaces. And in these settings, for 3AP, we know much better, but for general binary systems, the methods for 3AP, not clear how to generalize them, and our bound is the best known. There is some condition when we talk about general groups. And I want to mention new work that generalized the polynomial method for 3AP to another different class of linear patterns and get like very strong bounds over for the finite field settings. But this class doesn't include many binary systems. For example, K4 is not there, and larger cliques. So how do we prove such theorems? The main framework is pseudo-randomness versus structure, or in other words, might be a density increment argument. And let's see how it works for Watt's theorem. So we say that if A is 3AP, then it must be small. And denote the density of A by delta. And we can say, we can start with the following observation. If A would be random, with every element appears in A with probability delta, then we would expect to find some 3AP here. And if we started with large A, then we are done. And actually, we expect to see many 3APs. When we actually have this problem, we don't have random A, but we can say, okay, maybe A looks like random. So if it looks like random, this is enough for us. It would have 3AP, and we have to say in what sense exactly it looks like random or behaves like random. But let's leave it for later. And on the other end, we can say, okay, if it doesn't behave like random, then something else happened that help us. And thus we say, okay, if it's not pseudo-random, then we're going to find some structure inside it with density increases. So for example, the following set of points is not random. We can find some interval. This is, for example, an I structure for which the density of A increases significantly. So we find some subset B with density is at least delta plus poly delta. Now we can ask the same question and repeat with A inside B and ask, okay, A inside B, does it behave like random? We have 3AP, or otherwise we can, we say it's not pseudo-random and find even smaller structure. When would we finish? When we reach density 1, we will get 3AP and thus show that the set is not 3AP free. But on the other end, we might end up after a few repetitions, because the domain size decreases every time, we might end up with an empty set. So we cannot do it too many, we cannot repeat too many times. And in order not to, in our limited times to reach density 1, we need to start with some large delta. And this is what gives the quantitative bounds for different approaches here. As long as this is a density increment that we have, we cannot expect to start with delta smaller than 1 over log n. So just I want to emphasize that the main thing here is to show that we can be only in one of the two possibilities, either that this is the only two possible options, either it looks like random or we have structure inside with density increment. And in this point, Kelley Meka did a big step, and they showed a much better density increment. They showed that if A is not pseudo-random, then we have density increment which is constant multiplicative, or we can see it as additive linear in delta. And those, even if we have limited number of repetitions, the density increases much faster. So we can start with much smaller delta and still reach density 1 in our limited number of repetitions. This would allow them to get their bound. So why can't we just take their techniques and apply them for every linear pattern? So it turned out that they really used the structure of 3AP. They expressed the density of 3APs in A in terms of convolution, and then they used the properties of convolution in order to prove their steps, their density increment. And it's not clear how to generalize it to other linear patterns. So we want to use some different approach. This goes through graphs. So let me discuss this already was in the proof by Sam already that he showed he used the triangle removal lemma. So let us see our the graph approach to this problem. So we want to say that I want to show that every L3 problem for binary systems can be converted to graph problem. Let's do as an example the 3AP, and this works for every binary system. So let's recall how is the schema of 3AP looks like. This looks like a triangle. So we are going to blow up this triangle into a large graph that help us to solve the 3AP. For every variable, we put a cloud of vertices. Each vertex denotes settings of this variable. So this it's associated with elements in Zn. So we have n vertices, and n vertices for x2 in V, and n vertices in W for x3. When we have an edge, so between uj and vi, we have an edge if settings x1 and x2 to the associated elements in Zn would result in the linear form an element in A. This way, we build a bipartite graph between U and V. Similarly, between V and W, we do the same thing, but now with a linear form connecting x2 to x3. And between U and W, we do the same with a linear form x1 minus x3. This way, we get a tripartite graph. And the main observation here that every triangle in this graph corresponds to a 3AP in A. So now, instead of asking how many 3APs we have in A, we can ask how many triangles are in this graph. So just recall what is our goal. We translate our problem to graph approach, and we want to show some density increment. So we have to say what does it mean to be pseudorandom graph, and what will be a density increment. So let's start with pseudorandom graphs. We say that graph G with edge density P, this is a graph, is pseudorandom if it behaves like a typical Erdős-Rényi graph G and P, which is a random graph on n vertices, and every edge appears with probability P independently. So we have to say what do we mean by behave. So we take some properties of G and P and say, okay, if the graph satisfies this property, then it is pseudorandom. So first property is small discrepancy. All large sets of nodes, of vertices, if we look on the edge density between them, we have the edge density that we expect. By the way, these two sets should not necessarily disjoint. Another property that we can consider is that what's called all small graph count. We fix some small graph H, and we look into G. How many copies of H appears there? We can denote T sub Hg, the H density in G, is the number of copies in G normalized by the number of possible copies, and we expect it to be as expected in G and P. And a very surprising theorem from the 80s saying that these two properties are equivalent and as well as other properties. Let us see it formally, at least one side of the, of the equivalence. So these also are ideas that appears in even one a bit earlier work by Thomason. Let's see that P1 implies P2. So we think about a fixed graph, small graph H, constant epsilon, which is the error parameter, and then there exists some another constant delta. So let's fix some graph G on n vertices and think about n large enough, and which has density, edge density P. If the edge density in G deviates from what we expect, this means that P2 doesn't hold. Then it implies that P1 doesn't hold as well, meaning that there are two sets with the wrong edge density between them. This is a very influential theorem. And let me inspect the conclusion. So there are two cases. We might have too many edges or too little edges. So in the first case, we call it density increment. We have now subgraph that we can look at it, and we have more, it's much denser than the graph we started with. And on the other case, we call it density decrement. It turned out that since the sets are very large, every time we have density increment, we also have density increment, and we can forget about this. So now we should be very happy. We wanted to do density increment argument, and we have a theorem for this. So what's wrong? The problem is that our settings is for sub-constant values of P, and this theorem becomes trivial. So what would we want to have? We would be happy if we have a non-trivial condition, for example, making it multiplicative instead of additive. We would for sure pay also multiplicative in the conclusion. We can't expect otherwise. But it turned out that such an argument that would be very good for us couldn't hold. This is, there are some counterexamples, but what can we do? So if we pay in the size of the set, then we can prove such a theorem. And we called it weak sparse graph counting lemma. This already proved for the case that H is a complete byte-ablative graph by Kelley, and Meka. And our proof is actually easy generalization of their proof. So what's wrong? Why didn't we finish? So if we have density increment, we are very happy. But now it's turned out that density decrement, which is not good for us for a density increment argument, cannot be translated to density increment since the size of the set is not quite large. So what can we do? So this theorem is quite nice, not useful for our density increment argument. We still use it as a tool in our proof. But nevertheless, it turned out that even these large sets are quite large, and we can deal with much smaller ones. So if we allow the sets to be even smaller, of density P to log 1 over P, then we can show some what we call strong sparse graph counting. And in what sense it's strong? We can replace the density decrement, the general density decrement, by a very specific shape of density decrement. In particular, what we have is a set of vertices, a large subset of vertices that all of them has a degree much smaller than expected. And here this shape is really very helpful. Why? Because sometimes it just cannot happen. For example, if we start with a regular graph, all degrees have the same degree. Case 2 cannot happen, and then we have density increment. And actually, much of our effort was devoted to prove this lemma. So before I'm going to summary and open questions, just I want to note that one of the obvious open questions are improving the parameters, and in particular, if one can improve the parameters in lemma 2, this will be a really huge improvement in our bounds. In the summary, we saw a theorem. Our main theorem is Kelley Meka type bound for L-free sets whenever L is a binary system. We showed two graph counting lemma that works in the sparse settings. One is the weak one that gives either density increment or density decrement, and the lemma 2, the strong one, for at least regular graphs, gives us only density increment. There are some other results in the paper and more detailed lemmas. Regarding open questions, so additional other open questions would be, can we prove such bounds for more complex linear systems? So in our paper, we showed that our techniques won't work for systems like 4AP that has true complexity, a notion coined by Gowers and Wolf, larger than 1. And another question, can we show similar sparse graph counting for hypergraph? This would be help to handle 4APs, for example. And that's it. Thank you for staying that long with me.